Casey, thank you so much for joining me.
It's a pleasure to be here. Thanks for inviting me.
Perhaps I should give a little bit of a background to you. I found out about you first when you were doing that series of videos, programming a game up from scratch.
Yes, Handmade Hero.
Handmade Hero, and I've many times sneakily used your talking points in discussions of things like why is software so slow, and hopefully those are some of the same ideas that we can talk about during this live stream.
Sure.
My audience isn't necessarily software engineers, so let's try and make sure that people are carried along on the ride. But
Okay.
everybody interacts with software, and I think everybody has that niggling feeling in the back of their mind that something doesn't add up. Something about the world that we inhabit with software is not as smooth and wonderful as it might be, and maybe we can.
Well, I'm really glad to hear you say that because, obviously as someone who's worked on software for, several decades at this point, it's always hard to know what people who do not work on software, who maybe work on other things in their daily lives, but obviously now are forced to interact with software because there's almost nothing you can do that isn't, software.
Mm-hmm.
What do they think? Because, what they think of software, I don't know. And, I don't know how much of what I think about software is colored by my experiences with it as a developer. And so it's always good to hear that people are not happy with it because I'm not either. And so, it's nice to know that that's not a fringe opinion that only a developer might hold.
I almost wonder if it's one of these graphs where people who never use software see the problem. People who are, as you become increasingly expert, you start to excuse away everything, and then past a certain point of understanding, you then start to your eyes are reopened to the fact that, well, one example is the speed of hardware.
Mm-hmm.
Do you want to just give a bit of an illustration of how much faster computers are now compared to the 90s, for example?
Yeah, I mean, it's actually somewhat difficult to really express how much faster they are. It's worth noting, though, that so let me try and give a brief picture of the speed increase versus the workload increase, because there actually is a workload increase as well. And you do have to recognize that. So the easiest way to think about the workload increase is to look at the resolutions of screens. It's usually a pretty good way to internalize that for someone who hasn't really thought about this kind of scaling before. So if you go back to, you cited the 1990s. If you go back to the 1990s, that was a time when screen resolutions might have been 640 by 480, right? So 640 pixels across by 480 pixels down by 8-bit color. So, and I don't mean 8 bits red, 8 bits green, 8 bits blue. I mean 8 bits total, right? So index color. And most people today wouldn't really even know what I'm talking about when I say that, right?
Uh-huh.
Now today, if you go to look at even a bargain basement television, you can buy something that's 4K display, right? Which, I said 640. A 4K display is like double a 1080p. So it's like 1920 was the 1080p display. What is the double of 1920 in my head? I was just 3840, I think it is.
Yeah.
Right. So when you go to buy a piece of home electronics, you're buying something that has massively more resolution than what you look at in the 1990s. The reason I bring that up is because that's one of the major places that computers are now expected to do more work than they were in the old days. In the old days, you would not have expected a computer to drive a display with that many pixels in it. Now you do. And so there has been an expansion in workload in that a modern computer is expected to move many times the graphical workload than it used to. And this gets bad because each individual pixel costs something to process. It costs something for every pixel, which means that when you talk about a display like 3840 by 2180, whatever it is, you're talking about things that 16 times as much, 32 times as much. It depends. There's some high multiple there. And then you also factor in the fact that the color is, HDR or something. Again, there's a multiple there. So I would like to set the stage when we talk about computers getting faster, that there are certain places, display resolution being one of the major ones, frame rate potentially also being another one, et cetera, that depending on the context, people are expecting their computer to do more work. And you can't just remove that from the equation and say, hardware is so much faster now, programmers are terrible and they suck all over the place and it's awful because they're doing the exact same work so much slower. It's not quite the exact same work.
Mm-hmm.
That said, the advances in hardware speed have gone up so dramatically more than that, that it is almost as embarrassing as it originally sounded. Where did that speed come from? Well, there's several places that speed has come from over that time period. And I'll briefly try to give, is this too much information? I don't know.
No, keep going, please. Yes, this is great.
Where did that speed come from? There's many places where that speed came from. If you go back to the 1990s, some things you would say about the average consumer hardware. One, it was only a CPU. Typically, you didn't have a GPU. GPUs started showing up in the scene 1996, 97 in terms of consumer. They weren't commonplace until the 2000s. So you typically just only had a CPU. So one processor in a machine instead of two processors in a machine. All computers now have effectively two processors in a machine, the CPU and the GPU, even your phone. The only difference between these machines is whether those two processors exist on the same physical die, meaning are they welded together or manufactured into the same piece of silicon, or are they two separate chips, right? Mm-hmm. And on something like a phone, it may be very common for it all to be one chip. So you've got a CPU and GPU on one die. On a desktop machine, you also would have a separate GPU card that you plug in, so two completely separate devices. But either way, there's two totally separate processors that are that are separately programmable and each capable of handling workloads. That happened. Number two, CPU clock rates increased dramatically. In the 1990s, it wouldn't have been odd in the early 90s to see CPU clock rates of 25 megahertz, right? 25 megahertz. Wow. Nowadays, 6 gigahertz boost clock is a thing that would get thrown around, right? Like the Intel and AMD just, so you're talking about several orders of magnitude increase in clock rate.
So you've got enormous improvements in hardware and somewhat moderate improvements in capability.
And we're not done there. I'll just briefly mention core counts have gone up. That means that previously CPUs were able to do basically a single thing at once. Now they're able to do 8, 16 different processing completely different threads of execution at once. SIMD got added. That's the ability to do operations on multiple values at the same time. And when you multiply those together, you get something like a 64x increase just from those technologies. Then we got, I shouldn't say then we got, prior to that, actually, we also had this sort of superscalar revolution where CPUs began being able to overlap execution as well. So, you can throw around numbers. I should probably go build a diagram for you if you really want to know the answer, but we're talking about thousands to tens of thousands fold increases for workload increases of, max maybe 64. So by all accounts, your experience today should be so incredibly much faster than your experience was in the 90s, but that's really not generally the case in anything except for really maybe games where people are actively, what you experience in a game today is dramatically better than what you experienced in the 90s. And the reason for that is game developers have been pushing that optimization.
So, for example, if you wrote a piece of software in the 90s that took 10 minutes to load, it should now load instantly to human recognition if you just scale the times down.
Yes and no. I mean, that starts to talk about another subsection, which is the storage infrastructure, right? But that has had similar performance gains. If you looked at the difference, you would now be expecting, you can expect to get up to like gigabyte per second kinds of transfer rates. Nowadays, in the old days, you would have been expecting like between 1 and 10 megabyte per second, depending on when in the 90s you were talking about. So yes, I mean, basically the same thing is true for for loading, but for different reasons.
But it's no longer possible as a consumer to make the decision that you'd rather have the hardware running 90s levels of software, and you can't make the decision, I'd rather have the speed. Why have we used up every single ounce of additional speed on the computers? Where's it gone?
Well, I guess there's two parts to that question. I'll try to answer them in the order that makes the most sense. So the part one would be, where is the speed going literally? Meaning, what are programmers doing that's taking up all of that extra time? And then number two is, why is the industry in that state? Meaning, why are we doing that? And those are sort of two separate answers, I guess.
Mm-hmm.
So I'll start with the first one. So where the speed is going is really very straightforward. If you look at the, if you think about the amount of space that you're being asked to cover in software, it's massive. Software has gone from doing nothing for people to basically inserting itself into every part of human endeavor, including ones where it's not even making a benefit or where it's being detrimental, right? The jury's still out on whether Facebook was a good thing for humanity, but whether it was or not, it's here. Yeah. And so all of these things had to be built. And you're talking about going from nobody building them to building all of them in 10, 20, 30 years, depending on how you want to measure that time. It's almost a blip in human. So it's not even one person's lifetime. It's a fraction, a third of a human's lifetime, right? And to expand into so many corners of human endeavor so rapidly, I think it necessarily means you're looking at a system that doesn't really have much selection pressure. And that's sort of the answer, the second part of the answer that I'll talk about later. So when you're doing this, when you're rapidly sort of doing these things, it means that anything goes. As long as I can produce anything that looks like Facebook, that's Facebook. There weren't thousands of Facebooks, and only the best Facebook will survive. There's maybe 2 or 3 Facebooks total, and either all of them or just the one that's best will survive. But either way, there was not very many attempts. So when you look at a situation like that, what's going to happen? Well, the programmers are going to show up, and whatever they happen to do, they did. There's no reason for them to make anything better because they weren't forced to. Mm-hmm. What that means is anything that programmer happened to know. What did Mark Zuckerberg know when he started Facebook? He knew PHP. That was the thing he knew, which meant it was going to be the fastest way for him to put something together because it's what you know. What's the fast thing? It's what you know. And then Facebook ran on this giant PHP pile. PHP is a terrible language, extremely slow. And, off you go. Now, to drill a little more into the question, you're asking, well, why is it slow? When people make a technology, you interviewed Jonathan Blow before, and he objects to using the word technology in this case, and I kind of agree with him. PHP is not a technology. It's just a random language. People make these things. Somebody made PHP. They didn't have performance in mind. They sat down on a computer. They made some stuff. That stuff happens to be very inefficient. Someone else comes along, in this case, Mark Zuckerberg, doesn't know anything about performance, learns this language, can write things in it. They are very slow, but he gets it done. And now it exists. There isn't much competition. There wasn't some other group of people who really knew a lot about performance, who had made some performance-oriented language designed for web programming, where some other people who knew a lot of performance learned that language and then wrote a competitor to Facebook that would beat the pants off it because it was like instant when you clicked on it. That never happened. So as a result, when you think about this, getting to the second part of the answer, which is really the systemic answer, when you think about the process as a very much random Darwinian kind of process for how these things are produced, because there simply aren't very many things happening in any one space, the chances that you'll get something where people really knew anything about how to program or how the hardware works is very, very small. It's much more likely that someone who doesn't really know anything just kind of stumbled into it, tried something, they made it, it does work, and that's what you end up with, right? That's the much more likely outcome because it takes some amount of practice and knowledge and diligence to learn about the hardware, to learn about what's performant, and then to write code, using that. So I think when you take a step backwards and you just think about it as the stochastic process that, it's an industry marching forward that's covering a massive amount of ground, it makes a tremendous amount of sense why everything is so low performance. Because, how else are you going to cover all the ground? There's not this magical set of expert performance-oriented programmers that just flew down from the heaven on little angel wings and we're just all here ready for us to use them to make all these extremely performant products. So, I think that's where we ended up, and it's not that surprising.
Is it just a matter of knowledge, or does it take a lot of extra time and work to make something performant?
I would say there's sort of a question about what level of performance you're looking for. If you're talking about 10 or 100x faster than what we have now, no, it doesn't take very much knowledge. It takes some, but not that much. If you're looking for, I would like this hardware to be used optimally, it's almost so much knowledge as to not be achievable. And the reason I say that is if you take a look now, and anyone at home can do this, although it probably wouldn't mean that much to you if you weren't alive at the time. There are retro demo comps, they call them. These are things that take place usually in Europe. We don't have much of a scene for it here in the U.S. But in continental Europe, it's very popular. They are basically competitions where programmers try to make the most impressive thing they can on an old computer, oftentimes older than what you even referenced, not the 90s, but the 80s, sometimes the 70s, right?
Right.
And if you look at what they are able to accomplish, for example, on an original IBM PC, which I believe would have been from the late 70s, early 80s at the latest, it's astonishing. Nobody at that time ever could have done that.
Interesting.
Ever could have done that. Nobody did, and nobody even thought a lot of the things were possible. But thanks to modern tooling and many decades of study and what we've learned over the years from other things we've done that had nothing to do with that, you can now go back, take a literal IBM PC that is a physical piece of hardware, not an emulator, but literally the old IBM PC, just like it would have been that time, and you can make a demo that will do things that nobody thought it could do at that time. And so when you're talking about really maximizing machine performance, depending on the machine, obviously, some are simpler than others, but for most machines of non-trivial complexity, really maximizing it out is almost asymptotic. Like we may never really know quite just how far it can go. But to get that first 100x or 1000x over where we are today is actually quite simple. It just requires a basic computer education. Most of the things people say about it are false, in my opinion, because when people object and they say they're random quotes like premature optimization is the root of all evil, or well, we're just trying to get to market faster, all those sorts of things. Most of the time, they're thinking in their head about the kind of optimization that IBM PC retro demo kind. And I absolutely agree. It would be crazy to do that in a product space. I mean, that's ridiculous. But the kinds of optimization that I'm talking about to get that first 100x are just not doing stupid stuff. That's it, really. It's just taking basic account of like how this code should be organized for what it's running on. It's not actually that difficult. So you may wonder, why doesn't it happen? Well, again, there's this incredible startup bias to any one of these processes. If we go back to the example of Facebook, once you have Facebook written in PHP, you're not going to then start over the next day and rewrite it all in a sane, like performance, thoughtful manner. even if that would have taken the exact same amount of time, even if that would have taken less time than writing in PHP, the overall cost now institutionally to make that change, to get rid of all your PHP engineers and hire a totally new set of engineers, even finding those engineers, right? Institutionally, it's not really feasible. So although technically, if you had the people who knew what to do, you may have been able to just make Facebook in the same amount or less of time in a way that isn't horribly inefficient. Doesn't matter, because that's not a thing that really can happen, right? And so that's usually why people like me lament the state of sort of the education and onboarding process. A lot of these people are people who have gone through 4 years of college and don't even know these basic things, or they may know them in the sense that they had a class that mentioned them, but they don't understand how they relate to what they're actually doing day to day. Or they think, like I said, that there's some weird, it's like way too hard to do the stuff. It's not hard to do the basics. They're thinking of these, really advanced optimization stuff, which nobody is suggesting. And so, I think most of the problem is a pipeline problem. If our newer programmers were coming up with just a general basic awareness of how performance works, not only, I think, would we be solving this problem because they wouldn't be making as many obvious mistakes, but it would also put a lot more downward pressure on the stack. PHP never would have been slow in the first place if we had had a pipeline where nobody adopts a language with those problems. The people who made PHP wouldn't have done it because they'd be like, well, no one's going to use that. It's going to be dog slow, right? So there's a chicken and egg problem there too, where if the people who are generally your implementers who are showing up making these products don't know performance, then the stack also won't reflect that performance because the people making it don't know and don't think their customers care or their end users care, right? So there's a lot of problems in that that sort of need to get fixed systemically before it's going to move forward.
There is, it feels like there is a fundamental issue when people don't care. If you're as happy for something to load in half a second as if it loaded in one frame,
yes,
then nobody's going to put the effort to, even if it's a trivial improvement in the code, that trivial improvement will not happen.
It's not going to get prioritized by management. Nobody who does it is going to get a bonus or a promotion. And as hollow as that sounds, well, I mean, that's how you put food on the table, right? It's like if you're a programmer, that's what you're going to be assigned to do or what you're going to be incentivized to do in that sense, right? Meaning, excuse me, you kind of have this problem of the structure is not set up to reward the people who are doing the right thing. So as a result, they just kind of languish or are pushed aside, right? And the people who just do whatever the thing was that they were supposed to do, like move that box around or whatever, they're the ones you're going to end up with. So you do have that problem. I would point out that anecdotally, along the lines you're just talking about, I remember one time I did a video where I was like, hey, just so people know that, we're not making this up, here is a machine from, I think it was 2004. So, at this point, it's like 20 years old or so. Here's a machine from 2004 running Visual Studio, which is Microsoft's development IDE. It's what people use to program. Running Visual Studio from that era, Microsoft Visual Studio version 6, which is several versions, behind the one now. And here's how fast it is to step through a program. And you step through the program in a debugger, and it's instant. Just line, the watch window updating in real time. I can hold down the button, and you can just see it whizzing by. And then I'm like, here's the same situation in I think it was 2019, or it's 2019 or 2020. Here's a modern computer, at least 100 times, if not 1,000 times faster, running Visual Studio from today, debugging the same program. So I literally loaded the exact same program in, and I stepped through it, and the watch window can't even update. You step through, and you have to wait. You have to let go and wait for quite some time for it to update because, they kind of lost the ability to do real-time updates, and stepping was too slow. So I think they now just on a delay. So it doesn't even try to update it in real time as you step, right? And, you look at those things, and you're just like, this makes a really big quality of life difference to a developer. It's not acceptable, right? And you look at what you used to do. This wasn't a case. This is, the opposite of the Facebook situation. Here you took a performant code base and for some reason turned it into one that's dog slow for no reason. Like, I don't know why you did that. And that's a big institutional failing. Someone should care about this. Some developers from Visual Studio got in touch with me. I think I can't remember. It might have been. So I think it was unrelated to this. So I'm just going to pair those two things. At one point, I was complaining on stream about some Visual Studio slowness that I then later demoed this video. They got in touch with me and they said, "Could you please fill out this survey?" I swear to God, this really happened. I open up the survey and it says,
"Oh, this was related to how long does it take to load?"
Yes.
Yeah.
It said, "How long is acceptable for Visual Studio to load your project to open?" And the lowest answer was less than 10 seconds. It used to load instantly. It used to just be instant, right? And they went from instant to 10 seconds was the minimum they could. They can't conceive of a number less than 10. They're like, well, if it's less than 10 seconds, I can't measure that, right? So, it's really ridiculous because you're like, your own product from the same company doing the same thing used to be instant, and now somehow you've gone to 10 seconds. Where is the cognitive dissonance in your mind that you aren't terrified of that? I mean, if that happened to me in one of my programs where, day one it was running a certain speed and now it's running 10, 100 times slower, I'm freaking out. I'm like, what the heck happened? Like, I need to go investigate. They're just like, seems good. Like, no problem.
If your job is, I'm going to edit some text, fairly basic thing for a computer to do, right? You could load up Vim or Emacs or something like that back in the 80s and it would load immediately. You could just be typing and close the file and have the whole job done in seconds.
Yes.
Whereas now, editing a Word file is probably the most basic thing that an office worker might do around the world. It will take routinely 30 seconds for Word to bother to load up.
Absolutely.
Show all of its pop-up messages before you can do any. So it is having a measurable human cost in terms of just wasting everybody's time. And I'd argue for most people's use of Word, they could achieve the same thing with just text, just on a terminal command prompt.
Well, and it's also unclear why Word just can't be that fast. Word is not doing anything interesting at all, right?
Right.
It's a very, very basic thing that it's trying to do. Even once you start adding in some of the other things like pagination, there's not a lot of reason. And, mind you, we're not even talking about you could say, well, all right, maybe how much does it cost to paginate 100,000 pages of text? And, there's certain reasons when we talk about something like pagination, it's a linearly dependent kind of operation in a lot of cases, depending on how you want to define it and depending on whether the thing happens to have breaks in it and all these other sorts of things. We can start having a discussion about how hard it might be to optimize a real pagination problem. The Word documents people load are like 10 pages. It could repaginate the entire thing at 60 frames a second, no problem, if it was written properly, right? So we're not really in the realm of anything anyone's doing with Word where it could be plausible why it wouldn't always be basically instant. And yet, here you are most of the time in this hilarious situation where you're just sitting around waiting for something. You're like, how did this happen? And I don't know.
To some degree, I think the clear pattern is that the software has become more complex and we've been unable to manage that complexity, right? Somehow in the course of making this more complicated machine, we've broken it in certain ways that we wouldn't want to. If we could have put the brakes on and said, let's preserve our instant starting, it would have been possible. But in the course of the way the software was developed, that didn't happen. Is that a fair?
It's half fair and half not fair, maybe.
Okay.
The half that's fair is to say that, yes, if somebody had said, look, startup time has to be instant. So when you check in a new piece of code, if we've got a little thing that times the startup, and if it goes above 1 second, we disallow that check-in, right? So nobody's allowed to break sub-second load. Yes, then by definition, that would have fixed the problem, because all programmers would simply not be able to modify the program in a way that broke it. That said, the half that's not fair is suggesting that software complexity has something to do with it.
Okay.
The reason I say that is that if that were true, we would expect to see uncomplicated software right now still running as fast. Well, it would be hundreds of times faster because the hardware is faster. But that's not true at all, right? If you, for example, open up anything, and one of the best ways to look at this is something, for example, written on a web technology, in quotes, you can find incredibly simple pieces of software that are not complicated at all, that load very slowly and run very slowly. And so if complexity were actually what was causing the problem, then what we would expect to see is a range of software, some of which is fast but simple, and some of which is complex and slow. What we instead see is that all software is slow. And what that, to me, says is it's the first situation I described. It's simply that people don't know anything about performance, so they're just not likely to type in code. I mean, think of it this way. Suppose there's just a magic color. Red, green, blue, orange, black, whatever. We pick one color, let's say green. And if you happen to use the color green, everything is fast. All the people who know about the color green will just paint the thing green and it's fast. Everyone who doesn't will just be like, I don't know, I liked orange. And then it's orange and super slow. That's really what's happening most of the time. It's not that there was more work to do. It's you just had to know about the color green. And if you don't know about the color green, or don't believe there's a color green, which is, again, the common thing in software, people, they don't want to believe that there was a simple way to write this software that was actually fast. They don't want to believe that for some reason. Some people are that way too. Then you never will, right?
But partly you are, even if you're writing a simple program, you're still locked into a giant ecosystem, like this tower of layers and layers of abstraction. Time was when you would buy a piece of hardware and run a piece of software directly on the metal, whereas now, if you're running an application, it's probably inside a browser which is running on an operating system, and immediately even a hello world, you cannot optimize beyond a certain point, because you're just even an atomic piece of code is inherently part of a complex system.
It's true, but those platforms are not as bad as they appear. Right. So, if I decide to write something on Chrome, right? So I'm going to basically ship some web app and it's going to run on Chrome or Firefox or something. Is that not great for performance? Sure. It's not great for performance. 100% true. Is it not great for performance versus what you said, which was bare metal? I mean, sure, obviously, right? I mean, no question about that. On the other hand, it's not that hard to write something that runs at roughly 60 frames a second in Chrome. However, if you open up the average web application in the developer tools in Chrome, what you will see is hundreds of thousands or millions of lines of JavaScript packages that they decided to use. If they simply hadn't done that, they could have had a very performant web application, right? So even there, it's usually because someone just doesn't have any idea what's really going on. So they just pile all the stuff on. If Stack Overflow said, well, the easiest way to do X is with jQuery, then they just include jQuery and they don't care, right? Whereas it's like, you could have typed like 5 extra characters and done the exact same thing without including all that other stuff, right? And so you just keep piling more and more stuff on because you have no idea, A, what the simpler version would have been, but B, why you might or should have preferred that some perversion. And honestly, I don't think this actually saves development time, because what's the next thing that happens when you do that is now you've got bugs in React.js, or you don't know how one little thing works. So now you're tearing your hair out because there's no Stack Overflow answer about how, to move that button over to the side. And so, it's one of those things where like people are like, well, it saves me so much time. It's like, does it? I mean, I'd like to see the metrics that show that it does, because we don't really have those. So, I'm fine with people using libraries, but you have to demonstrate that it's actually an improvement.
It's difficult to find the right halfway house, I think, because I guess the one extreme is you hand roll assembly for every processor and have no operating system. That's like the straw man extreme to one end. And the straw man extreme to the other end is, I'm going to use the web framework of the day, and I'm going to import
more than one. I'm going to use several, right? Sometimes, right?
And I'm going to download a library that I'm going to use for adding numbers together, and et cetera, et cetera. And between those two, it is the case that you're going to be more productive going with the tower of abstractions than trying to build stuff completely from scratch. So it's understandable why people develop this intuition that reusing other people's software is a shortcut to productivity.
So I guess there's a couple things to say about that. The first one I would say is that only makes sense if you take the people making the frameworks out of the equation. Because, for example, React.js did not come out of nothing. It's not like it just, we were, Joseph Smith went up on this hill and dug in the ground and found React.js, right? It's not like it's not like a prophetic thing that we just happened upon it and I don't know, it came from God. It's like, no, we made, right, this thing. And so why did they make it so slow, right? Like you have to ask the question of, somewhere down the line, someone's responsible. Even if you want to absolve the person who uses React.js, you have to ask why the people who made React.js didn't make it faster, or things like that. But assuming that you don't want to do that, I agree with you that if you decide to take the exact polar extremes, what you said is probably true, because hand rolling assembly is very difficult to do, and there's not that many people who can do it. I wouldn't necessarily even say whether it's about fast or slow. It's just, it's harder. It's a skill that less people will possess. So I don't think that there's much possibility that you could staff a company with hand-rolled assembly kinds of people, right? Now, fortunately, there's no need for that. We're just talking about basic stuff. I'm even saying, even if you decide to use JavaScript, you could do much better than you're doing now. So I don't really think we have to talk about it in those extremes. That said, I would point out that there's a missing element to that equation. And I would liken, so it's not clear in the short term exactly how valid this analogy is in toto, but I would liken it to the 50s or so, in terms of industrial pollutants. So in the old days, you would just be like, well, we're making these chemicals at the chemical facility, and then we don't need this waste product, so we dump it in the river, right? That's the modern model of programming. And what's the chemicals and what's the river? The chemicals is that wait time, the delay, the increased performance cost. And what's the river? It's the user. Not having to train programmers to do a good job, or not hiring performance-oriented programmers, or not taking some extra time to do that if that's what we need. The company is saving itself money and time by costing the users money and time, right? It's basically what they call an externality, right? And like I said, the externalities, I was kind of alluding to this earlier, they won't get corrected in a market until there's something forcing them to be corrected. Now, in the case of polluters, because the market dynamics are difficult, because a polluter would not have been required to disclose the fact that they were dumping all of their chemicals into a river. And so what had to happen in that analogy is, like in America anyway, the government had to create some regulations. They had to say, you can't dump things in a river. Or in other cases, maybe they would force you to label it that you put a big sticker on the product that's like, this thing uses toxic chemicals or whatever, so that the market could then, humans could decide, I don't want to buy that thing, right? In the case of software, it's unlikely that a government agency is going to step in and place a label on a product that says this thing's a piece of crap. But
we've got warnings that pop up, legally required warnings on websites if they use cookies. So I guess that was an example of a technology that was considered too evil. But it should be a pop-up that says this website uses jQuery. Are you sure you want to continue?
Well, we've got that pop-up. Amusingly, it's just not from the government. It says, this tab is taking a very long time to respond. Would you like to close it? Right. But that came from the browser vendors. No, so what I was going to say is I think the likely outcome long-term, because remember, we've only seen a short window of this. It's been a very short time of this really performance unaware programming of about, 10 to 20 years. Long-term, I think it's just a market correction. Long-term, people will start offering competitive solutions that are higher performance, and they will just replace the old ones. I think we've seen that happen already. So as soon as it does, it will occur. I mean, you can easily point to things like, one of my favorite examples is Google Maps versus MapQuest. MapQuest just showed a static map, and if you wanted to move, you clicked a button to like scroll it, and it would like page in and like boop, 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 right? Google Maps came out, and the only thing it could do differently is it smooth scrolled. You could drag and it would page in as you went, right? Minor change in performance, but it increases the frames per second to the user to like 10, 15 from, 1, right? Everyone switched. Instant. Why? Because people naturally respond to performance. My other touch point, iPhone. Windows CE did all the same things that an iPhone does. Did more things. Like you could run spreadsheets on it and stuff day one, right? Mm-hmm. What was it? It was dog slow, right? You couldn't touch it and like drag things around at 60 frames a second. Out comes the iPhone, and what can it do? Basically nothing, but you can drag things around at 60 frames a second. Everyone wants it. It just feels awesome to use. It's great, right? And by the way, it also opens up new possibilities. Okay, now we can have games on there. Now we can do, right? So performance is its own selling point. The reason that we're even having these discussions or in the programming sphere arguments about it is simply because performance-oriented programmers haven't descended on a particular industry. If they do, the rest of the players will be removed basically instantly. I don't think it's really that big of an issue. So when people like me complain about it, usually we're complaining from the point of view of a user, right? I'm basically saying, hey, I am sick and tired of using all this stuff. Why are you guys such slackers, right? I'm not complaining about it from the point of view of a developer, because as a developer, what it actually is for me is like job security. It basically means that at any point, if I need to make some money, I could just go take over one of these businesses by just shipping a 10x faster version of what they do. That's great. It's an opportunity for me. So as developers, having to use the software, it's a bummer. As a business opportunity, it's actually great. It means that anyone with a mind for performance, the world is your oyster. You could go choose anything that's being done right now outside of basically like games and some small side of server stuff where people just have no idea what the heck is going on. And you could just go in there and just own them all day long, right? And so that's kind of reassuring, because it means that if you are a performance-oriented programmer, good news, you could probably start a company just to target performance, and you don't have to be creative. You don't have to think of a new product to make. You can just copy someone else's.
This problem has been apparent to anybody with their eyes open for, at least 15 years, I would say. Like, why?
It gets increasingly worse, so it gets more apparent every day, right?
Yes, but nonetheless, if this is such a gold mine of opportunity, why hasn't this already happened? Like,
again, just it's supply and demand. There just aren't enough performance-oriented programmers. When they do focus on something, it's a big deal. I mean, people are really interested anytime someone, there was a thing, recently where someone was like, we have a faster JavaScript runtime. This was huge news. Everyone was like, oh my God, right? It's like, you can make, what does this thing do? Nothing that hasn't been done before. It's literally just a replacement for some other thing that already does all the exact same stuff. What was the improvement? It's faster. That's it. That's the entire raison d'etre for this entire company, right?
Mm.
And that's a thing you can sell. You can literally sell bare performance. That's how bad this industry has gotten. No new features. We have 0 features. All we are is not dog slow, and that skates. So again, I think it's just supply and demand. There aren't
That,
enough people who know how to do this stuff.
it, that might work in the case of a JavaScript interpreter. Like, isn't that just software becoming similar to hardware in that hardware has been doing great work at improving in speed? It's just allowing more people to skate by on the top with poor application level code.
I guess I would say that doesn't really bother me that much. I care mostly about whether the end user experience is good. And so I don't really care how we get there. If someone can figure out new ways of allowing people to really not know what they're doing at level X, right?
Yeah.
But at level X minus 1, like right below that, we can somehow fix it. Great. My objection to any of these situations is only when the end result is too slow. So I don't actually mind that. That would be fine. I think most of the problem today is that the assumptions there that people make, like, oh, well, this will be fast enough. It's not. It's not fast enough, right? That's the problem. If those assumptions start becoming true because we can replace the underlying stuff with magical compilers that somehow turn all this code into something usable, that's actually great because it solves the problem. I don't have an ideological angle to any of this in my mind. I
Mhm.
just want the end result to be performant. And however we get there is fine by me. And if we can do that, then I have no problem with application layer programmers having no idea what they're doing. If we can make that work, that's fine with me. We just haven't yet. That's all.
What I'm concerned about is that the performance issues are all in the application layer, and that the reason that they're slow is because the applications that succeed are mostly determined by the biggest companies with the biggest marketing budgets, and they don't know how to select for effective programmers because it's impossible to find them through interviewing. You can't tell until they're in your company either doing the good work or not. The managers can't properly code review. You don't know how productive somebody is supposed to be in terms of features per week or anything. It's like a big unmanaged mess for the big tech companies.
Yeah, I mean, I'm sure you're right about that. And I guess what I'd say is I do think markets tend to correct those problems longer term, though, right? I mean, I do think that overall, if your company turns into the equivalent of an IBM, right, is sort of what you're describing, right? It's like we just get very large and there's a bunch of people here and they're just like a self sustaining cycle of managers talking to other managers and people like billing consulting hours to some government somewhere that doesn't care, which is basically like IBM today, right? I mean, except for their patents division, right? um that's totally fine. That's a corporate structure that can exist, and you're probably right that that's going on at some places. Google might be a good example these days. It seems like they've kind of fallen off a cliff. They were originally sort of this company that was doing a lot of it's like I said, they were the ones who brought us Google Maps. Like, how do you do a JavaScript web application that actually is running really fast? That took some doing, right? And now they're kind of the company that's like, well, we're pleased to announce our 17th rebrand of the thing that lets you voice chat.
Yeah.
Here's your notice of that. And you're just like, what is happening over there? So yeah, it's these places can definitely get into those situations where they're just, they just decay over time. It's probably true. But like I said, I'm not that worried about that because I think any one of their things is assailable from a performance standpoint. I think that's generally going to be the case. I think the monopoly lock-in on performance being bad is not so great as people expect. Maybe there are some things where that's true, but I don't think it's that likely. The other thing I would say is these companies seem to fall all over themselves anytime there's a new buzzword X, whatever that is. So I also think there's plenty of ways to attack the status quo from the outside. If someone shipped a massively performant JavaScript library for UI, these people would adopt it, right? They're not sitting there wanting to suck. What they're doing is they're just defending the way that they do things, which is by using existing things that they themselves don't know how to build or don't want to rebuild. And they're defending using those things because it's easier for them. That's all that's really happening. I don't think they're sitting there saying, I want my software to be bad. So I think if you offered them the opportunity to reuse software that was better, they would take it. I really do think they would.
I guess the different options for technologies compete with one another on multiple fronts. So perhaps there might be a more performant framework that's competing against one that's easier to install, or there's a framework that cares more about users' privacy. You know, it's got lots of security features, but that's competing against another one that is, you know,
advertising friendly.
Yes. Well, right. Yes. So in a sense, people will say that they want to work with a performant solution. It's a bit like people say that they care about their privacy, but in practice, they will always pick convenience. In a sense, as long as there is an option that means that you can go home earlier from work, get an extra hour out of the office, it's going to be very difficult for someone to compete on purely. I mean, you see this to some degree with, say, YouTube, right? Is the go-to video streaming platform. There's plenty of problems with YouTube. There's reasons people want to quit and go to other platforms, and yet, despite whatever hard work their competitors put in, they can't match feature for feature. And people want to jump ship. People are trying to jump ship from Twitter. A different set of people are currently trying to jump ship from Twitter than were a year ago. But in neither case did it really work, because there were other factors that were overridingly important that crowded out the competition on the whatever metric you wished was going to end up winning.
I absolutely agree that anytime you have something like consumer choice or adoption, or in this case, developer choice and adoption, in the case you were talking about with frameworks, for example, it's a multi-factor analysis, right? They're going to weigh multiple things, performance being one of them or whatever. I don't disagree with that, but I think the case for performance is being understated in what you're saying. And again, I'd like to keep hammering home the example of the iPhone. When the iPhone came out, it could not do anything.
Yeah.
Windows CE could run almost every piece of software that you can run on Windows typically. It had spreadsheets, it had word processing, it had email, it had everything exactly the way that you were used to doing it. It could interact with Exchange, it could do all these things. iPhone comes out with 0 features. It only has like a basic built-in mail app that doesn't work with anything, a basic built-in web browser, and phone calls. That's what it had. No app store. Yeah. It was adopted immediately by everyone. Everyone wanted that device as fast as they could get it. It destroyed entire markets. BlackBerry disappeared because of iPhone, right? And BlackBerry was entrenched in everything, in government, right? And so that was a different, so just bringing that up because I keep saying Windows CE, but BlackBerry was massively entrenched and it destroyed it too. So 2 entire ecosystems destroyed by something with nothing but performance. So I think performance is its own argument, and it's a strong argument. Just nobody is providing that option. It's just not what that sphere does. It's what games do. That's what they sell a lot of times, is performance. So you see a lot of it there. Nobody sells it anywhere else. And until we start making that argument, I don't think we can really criticize full-throatedly people who are choosing to use React.js or things like that, because where was the super performant option that we offered them? They might have taken one with less features that was more performant. They never got that choice, right? So I think it's like, it's not really fair to point the finger at the people making these decisions, because they don't have the capability to do that performance work. We're saying that a priori. So if we never give them the option of choosing a performant option, is it really their fault? I mean, in a vague sense, you could say that it's institutionally their fault, but it's not like the person really had an option themselves, right?
The thing I think is remarkable about the launch of the original iPhone is there was almost this heroic act of will to create something radically simple, and it was the bringing of order, in the sense that it's when something becomes disordered, it increases in the amount of information, right? You get more stuff, more clutter. And that's what does tend to happen with technologies. You build something at first that's beautifully simple, and then over time, extra features and extra craft gets accumulated onto it. And it's very similar to the basic law of thermodynamics, where things just become disordered over time. And the iPhone was this moment where, kind of like a beam of light shining into history, you get this like sudden radical reappearance of simplicity in computing, where you had a device that you could hold in your hand that was a computer, but it only had a limited amount of options for what you could do with it. And it was actually it always strikes me as it's kind of strangely backwards and odd when people do announcements about the new features that they've added to their product, because in a sense, if you have the same product but with more features, it has degraded the product. It's like it's become harder to use. So there's a way in which the iPhone was not just offering performance, it was something tangible. I think people can appreciate a simple, straightforward. I mean, physical objects are simple and very reliable, and you understand how they're going to work. Digital objects are often full of unwelcome surprises.
Well, I think, again, I would turn that around and say further evidence to me of what I'm suggesting. If it turns out that simplifying things is also a separately desirable consumer proposition, then there's even less reason to issue performance, because we're saying not only will your simplification efforts be rewarded because the software can be made faster and you can concentrate on more things, and it's easier for you to develop a competitor to something because you don't have to duplicate all the features. Well, now you also are offering a bigger value proposition to the end user, because it's like, I don't have to look at this massive sprawling React.js anymore. It's just got these few simple controls that I use for everything, and they're nice and streamlined. Great. As a designer, now I'm happier too, right? So I think that, like, again, that, if anything, argues in favor of performance being a viable option here, because if simpler's better, well, simpler's better for performance too. And it makes it easier to create a duplicate product because you can duplicate less. I mentioned one thing, by the way. I noticed in the comments people were mentioning BIOS. And I would actually object to using BIOS as a counterpoint. The reason for that is I also had a B-Box for a while. It wasn't ours, but it was in the office. And if you used Windows and then you went and used BIOS, you didn't really notice much difference. Yes, a trained developer could think about why it was faster and go, oh yeah, this is the dual processor nature is a little bit better and these things are a little bit better. But the actual end user experience of using a B machine, no one would know. They just wouldn't. It's like, you'd have to be very observant to really know the difference. And part of the reason was because back then Visual Studio stepped instantly, right? Like, a lot, BIOS today, the difference in BIOS today might have made a difference, right? Back then it simply didn't. So I would actually object to that difference. I was there at that time and used machines. None of us cared. We used it in the office and we're like, all right, same actually thing happened with Alpha. I don't know if any of the people remember DEC Alpha. You could run the FX32 compiler and you could run Windows NT with FX32 compiler on the DEC Alpha, the transpiler, I should call it, I suppose. And you could just try the experience. The Alpha was a much faster processor, first one to hit 1 gigahertz, I want to say. It was at least it was about twice as fast megahertz wise as an Intel processor would have been in those days. So, it's at least 600 or something. I don't remember the specifics. Again, not fast enough to really matter to the end user. It's hard to overstate the jump between Windows CE and something like iPhone or MapQuest and Google Maps. It's not a 2x increase. It's a 10x increase. There's a big difference between those two things. It's hard to come at somebody with it's 40% faster. Okay, maybe that's good enough. Right now, like I said, you can come out with something 100x faster. That's a consumer advantage.
Yeah, we saw the power of simplicity, especially related to compute speed, in the battle between RISC and CISC processors, right? It turned out, as you maybe would hope, that the reduced instruction set had all these kind of benefits, and I guess that's what. Well, that's what we're. You're not convinced?
I mean,
it definitely won.
No, actually. So it's sort of at the moment, I guess you might call it a tie, depending on how you want to look at it. So, it really depends on how you look at it. So you could probably make the argument that RISC quote unquote won because GPUs are sort of closer to RISC, but do you actually want to go down this rabbit hole or not? We can go down this CISC versus RISC. It's a very interesting topic. I don't know that anyone watching will care.
Why don't you give a 30, 60 second?
Okay. So we'll start by saying, obviously, you've got two different competing CPU lines right now for performance. One line would be AMD's Zen 4 cores, which are CISC instruction sets that translate to micro-ops internally, which the micro-ops are RISC, but this is done very deliberately and in a specific way. So the CPU is still CISC. You are feeding it what amounts to a compressed instruction stream, which is what CISC sort of is. It's basically like it blows out into more RISC instructions, right?
Mm-hmm.
And then you've got M1 and M2 from Apple, and those are closer to RISC instruction sets. They're ARM-based, but even ARM uses things like compressed encoding and things like the, SVE. Like, is that a RISC instruction set? There's all these things in there where you're like, okay, do you want to call this CISC or RISC? Is it really a RISC instruction set? The neon instruction set, is that RISC to you? Maybe. I mean, how do you want to define reduced when your thing has, 500 instructions? How reduced is that, right?
Interesting.
So looking at something like that, I would say I don't think RISC won by any stretch of the imagination. You could say that it's maybe a tie or that we don't know yet, but saying RISC won is tough. And then if you look over on the GPU side, it's like, well, what part of the GPU are we talking about, and what do you consider the instruction set? Technically, the instruction set to a GPU is the shader IR. There is a compiler that sits between you and that hardware. Talk about CISC as a model for programming. They not only wanted the ability to have complex instructions, they wanted the ability to have the entire loop sent to them raw, and then they can change it with every GPU. Is the GPU under the hood RISC? Sure. Is the programming model RISC? Not even close. It's the opposite of RISC. It's the most CISC instruction set ever devised, and that's currently what we use for performance-rated programming. So it really depends how you want to slice that apple.
I guess the argument would be that in both cases, at some point, there is a RISC bottleneck, even if it's not one that the instruction set relates to. Like there's this sort of set of compilation steps that eventually pass through something that can be reasoned about, and therefore the people who are implementing the hardware can perform, more effective speed optimizations because they have a known quantity that they're optimizing on. Is that a fair concept, that the reason that the hardware is able to be optimized is because you've in some sense got a limited set of instructions that could be coming in?
I mean, again, I would say it's kind of a distinction without a difference. Like, nobody would argue, even in the most Siskian times of thinking, that somehow, like, you weren't going to end up with a multiplier on the chip. Like, we all agree that there's going to be that circuit. So if the idea is that, well, what we mean by risk is just that there will be execution ports at some point, and those execution ports will probably just have like 30 or 40 instructions. I don't know, like what's the breakpoint? I mean, like, just let me give you a simple example. Okay. Would anyone have considered it to be a risk operation to have a single instruction that takes a register with 16 different offsets in the register, fetches 16 different memory locations off of a base register, combined with those, reassembles them into one register, right? And puts that back into the register file? Is that risk? Because if that's risk, what's not, right? And so everything has that. ARM has that. x64 has that. GPUs has that. So where's the risk? Where's risk, right, in this? So I would almost say, like, to my mind, CISC won. If I had to say which one, to my
because
mind,
you've got floating point unit,
everything's in there. Oh my god, right? I mean, there's you look in these chips and you can find all these just like RISC-V. It has risk in the name. Their vector instruction set, the only one they have, RISC-V, it has an instruction that lets you gang multiple registers together to produce wider operations. How the hell is that risk? That's the most Intel in their wildest dreams never ganged multiple registers together with a permanent setting. Like, that was not a thing. I can't think of anything in x86 that ever let you say, this register, and this register are now all going to trigger when I do this one instruction later based on this instruction I said before. So to me, it's like risk. To me, risk is dead. It didn't work. CISC is the only thing people are using now. That may be because I look at it differently. Other people might say, nah, that's a dumb way to think about it. And I wouldn't argue with them because it's just a label. And I don't really care. The underlying truth is what the truth is. And whether we call it CISC or RISC is somebody's pedantic argument. But to me, complexity is all we see now. The reduced thing is nowhere to be found, to me. The mentality, anyway.
Is that because the CISC approach proved itself to be advantageous, or is that just the direction we've gone in?
I mean, again, the reason that I say I think CISC won is because when you look at what a lot of these modern high-performance chips need to do, the instruction decode time is non-negligible. It's simply expensive to load instructions into a CPU. I mean, I could argue that the RISC versus CISC battle was lost the day SIMD happened, because SIMD is specifically about saying, oh my God, we can't afford to decode all of these multiplies and actually pull the stuff that we've got to make things that operate wider, because if we don't, we'll never get the throughput up for things like IEEE float performance. And so to me, like, RISC was just dead in the water. It's just not a good idea, because the fundamental idea to me, what RISC means, is keeping everything as simple as possible because it's faster. The truth is the opposite. You need some amount of complexity because you need to be able to look at where the things are that are costing you your circuits and say, we're going to optimize the instruction stream to get rid of those points. That's a CISC move, right? So I totally agree that, like, very long instruction, like VLIW or something like that, totally failed. Like Intel Itanium going nowhere fast, right? So the super sysc, like we're just gonna just do ridiculous crazy instruction streams that encode 50 different things about how did I want you to predict the branch and do this load depend on the other one all in one instruction. I agree that didn't happen, but complex instructions, yeah, we've got them and they're here to stay, I think.
I mean, that is an interesting conclusion to come to if we return to the world of software, because it sort of implies that I think there's a kind of pleasing elegance that made me want to conclude that
what were those? Sorry to interview you on your interview, but what were those?
What I mean is that the risk idea is appealing because it's nice to imagine that you could have a simple idea and get practical outworkings from it, and it's kind of ugly that we end up having single instructions that take multiple clock cycles to execute and things like this.
I see. Yes.
So it's like nice to imagine that the world ought to be simple. And I think if you go back to the software world, maybe there's a similar situation where there's kind of a dream of, wouldn't it be better if, and actually that's more based on our human concepts of beauty than actual practical, the real best case of how computers could be organized maybe is closer to the way they are organized than we would like to think.
Well, I think I would just say that every, boundary that we're forced to define. So, what we're talking about here is the boundary between the software side and the hardware side. That's what an instruction set is doing, right? And ISA is one way that we have a boundary between hardware and software that we need to communicate across.
Mm-hmm.
Everywhere that we have that, API boundaries in software, ISA boundaries in hardware, whatever you want to call it, there is a level of communication that optimizes the typical use case for that thing. And I just don't think it's in any way unappealing or less elegant to simply say there is no inherent favoritism between simplicity and complexity in that trade-off. It is simply a case of how flexible does this communication need to be for the use cases that we are optimizing for. And that will not be the simplest, and neither will it be the most complicated. It will be somewhere in the middle based on the typical needs. And, you can see this very simply. Do you think that a graphics library should accept the ability to draw a rectangle, or do you think it should have to call to set each individual pixel, right? Setting each individual pixel is more risk and more simple. You can certainly draw a rectangle that way. Is that the efficient communication? No, because we often draw rectangles. We often draw them with a coherent fill pattern that we know ahead of time. And so it is simply wasteful to think that we have to say every single pixel in this rectangle every time, instead of just clearly delineating the two boundaries in the Euclidean plane that we know we can do quite efficiently. And so to me, those aren't bad things. The fact that the simplest possible thing is not the right answer isn't bad. It's how it should be. They're two ends of an extreme, and risk versus sys to me is always just about, well, yeah, we're not going to do either completely. We're going to pick the right, the optimal thing is to pick right in the sweet spot where instructions are as complicated as they need to be to make sure the chip can operate as efficiently as possible, but no more complicated, right?
Yeah.
And that is exactly what you're trying to do anytime. It's always a balancing act, and you're trying to be somewhere in that hot zone.
But we are inherently progressing along a path where we try to create machines that do everything, satisfy every use case, and the decisions of what is priority or not is a sort of committee decision. And this does seem like a bit of a recipe for disaster. And
Sure.
Maybe an interesting case in point is the current spec for C++, which is so bloated with rubbish that it's difficult to argue that it is the optimal solution, but it's got all this historic cruft in it, and for various reasons.
Forget historical cruft, modern
New
cruft as well. We
brand-
don't have to go back. You
factory fresh cruft.
The cruft comes right with the freshest draft. Every new page is cruft of the C++ standard.
So it's I guess there's a bit of an engineering dream that you could imagine deciding I want to make a spec whereby you have to give pixel by pixel instructions, because I'm just going to disregard high speed, high refresh rate something as one of my use cases. And then the positive side effect of cutting out that use case is that now you don't have to rely on a graphics library, and now you don't have to. Now you can implement your code directly addressing the screen, instead of indirectly going through this thing that's full of its own bugs and trade-offs and ideologies or whatever. Perhaps there, if we stuck more to our guns and said we're going to write beautiful code and we're going to ignore the I guess this is very much going against the grain, because so much and for very good reason, we are pushed to think user first. Every decision we make should have the end user in mind.
Wait, who is pushing? I never hear anyone say that. They're always thinking of the. No, seriously, I've never heard anyone say that. Like the C++ committee, I don't know that they've ever thought of the user, ever, not once.
What do you
mean
think
by that?
The C++, the steering committee, who would they say is
them?
Like, what's their objective? What in
their weird ideas about like spec purity thing. I mean, I have no things that should be absolutely trivial and should have been solved years ago. Like, I would like to include this binary blob as an addressable variable in my program. Like, they're still arguing about it now.
Yeah.
Right. So if the user, if your goal was user first, we would have had that in 1988. Right?
Fair.
Because it's critical, right? Like, everybody needs this feature. It's critical. Everyone has to come up with a workaround for it, right?
Mm-hmm.
Everyone from game developers who want to include some binary data to web developers who want to include a little bit snippet of text easily. And like, it took forever to get here docs, and we still never got embed, and now they're arguing about embed even to this day. Like, we're finally going to get it in like the next spec or something, supposedly, or something. I don't even know. And it's just ridiculous. That's not user first, obviously. It's them first, them thinking about something, and I don't know what that something is. But it's ridiculous, whatever it is.
But regardless of all its deficiencies, C++ remains the industry leading standard across all types of software. Not every type of software, but anything remotely performance related, you're going to probably be using C++ to this day. There are competitors which have all sorts of interesting claims, cleaner, easier to use, but the community is overwhelmingly still in the C++ world.
Well, I mean, that's really just something that people will have to take over a long time period. C++ took, I mean, what is C++, 1984? Or
I don't know.
When was C? I don't know when C with classes was introduced, but it would have been sometime in the mid 80s, right? Is C with classes. It took decades for it to get where it is now, and all of the tooling that's been built up around it, and IDEs and all that stuff. So is it, a dying language? Absolutely, I think. There's no question that C will be replaced over time. It obviously already was replaced in a lot of spheres, in that like Python programmers and JavaScript programmers don't care at all about C++. So in certain spheres, it's been completely replaced. Nobody talks about it in those spheres. But in terms of the spheres you're talking about, where people are doing more low-level stuff, systems programming, game programming, that server side stuff that's, performance critical, whatever you want to call that stuff, is it still the totally entrenched standard? Absolutely, but it took decades to get there. People are now finally starting to say, hey, this language sucks and it's causing a lot of problems. We should start trying to replace it. that work will also probably take decades. Now, it might not take as many decades. It might take 1 decade instead of 4 or whatever, because things can travel faster now. The internet has connected us. We don't have the situation in the 80s and 90s where things traveled on a floppy disk. So it's possible that it could spread more quickly, as did something like Python. Python did not take 30 years to become an entrenched standard programming language in various places. But I think it still does take 10 years. It wasn't like Python showed up and then it was 30% of all programs, the next week. So when people look at the languages being created now, that's just the first step in this long process. And it's going to be a hard process because it has to actually be good on some objective measures. Python, for example, just had to be the best language for cobbling libraries together. It was fighting with, right? That's what it does now. It had to fight with PHP, it had to fight with Perl, it had to fight with JavaScript or whatever. They had this big battle of who was going to be the scripting language of choice, and Python, maybe sometimes JavaScript, because of, it's got it in, Python isn't embedded in the browser, so it has sort of unfair advantage there. But that's what we ended up with. Python and JavaScript, those are your scripting languages, right?
Mm-hmm.
And that's easier. It's easier to be the kind of crappy language, but we have a great standard library, which is kind of how I would define Python, right? It's pretty easy to grab something that does what you want and string it together with something else, and that's what it was supposed to do. It sort of works. It's very slow, unfortunately, but it sort of works. So there you go. Replacing C++ is harder. It has to actually satisfy the goal of being able to do low-level programming, to have rigorous type checking and other sorts of security-based features that C++ isn't even that good at, right? But you look at something like Rust, that was their big thing they were trying to do, right? Is like, we'll make something that's like not necessarily much better than C++, but it's, designed to have these extra safety goals or whatever, right? And they probably think it's better than C++, but whatever they want to claim, it's clear what they were trying, right? And so that's another aspect that you could think of as needing to get right. That's a lot harder. No one's talking about whether Python needs to be safer, because Python's a disaster, right? It's this giant, of course there's going to be security exploits in a Python thing. For God's sake, you're using so many libraries. If any of them have a security exploit, you're done, right? So it's a different sort of domain. So I do think people have to be realistic about the time frame. If you want C++ to be replaced, it's not going to happen next week. So the work is starting. It may be that the language that replaces C++ hasn't been made yet, or it may be that it's one of the languages that's coming up now, but it's going to need some time. Either way, I don't think you can expect to have a replacement for C++ next year, right? It's going to take maturity. It's going to take tooling. People have to get acclimated languages. They have to start being taught in schools, all that stuff, right?
Can we talk a little bit about programming paradigms? So it seems I've done work in a bunch of different types of software, writing games, bits server-side cloud infrastructure. I've done front-end web work. I've done, and wherever you go, there seems to be a little culture that's developed with its own set of tools, its own set of predilections, and in some sense, they work with one another. So if everybody in that sector is using a certain tool, it then leads to certain language features becoming more appealing, and vice versa. So actually, what may be a really obvious no-brainer within one sector looks foolish from another sector, and I there's maybe partly that is influenced by the type of work that you need to do. I guess if you're prototyping and throwing something together that doesn't matter, maybe typing is less important, for example. Maybe there's a reason that Python has taken off in ML world, where they're just playing and then they hand over to somebody to re-implement it when it goes to production time. But I think partly it is just arbitrary. We all use this set of standard things, and therefore we all can talk to each other. But I think there are some bits of programming practice that are actually quite poisonous. And
Okay.
it's very difficult to spot them because we're not very good at measuring, how do you compare the implementation of a certain set of requirements, given that it's probably only going to be implemented once, and you're then comparing to something different. So some of the ideas that seem to have risen and falling are like object-oriented with a heavy use of inheritance, which seems to have been a complete disaster. And then functional programming, which I got at one point very excited about and invested a lot of time into investigating. And for one reason or another, I now think was largely a dead end idea.
Yeah.
So are we actually making progress in these more sort of ethereal programming paradigm type ways, or are we going around in circles and chasing our tails?
I would say probably the latter. So I think there's a couple mental things that go on with these languages in general that are... This is kind of a difficult topic to explain or discuss. The reason for that is because all of the stuff that happens is mental linguistic operations. And I'd like to draw a very clear distinction here because I think there's something that people don't really appreciate about programming that is very important. So we all agree, or at least hope that we agree, that the programs that we are able to make on a computer are specifically those defined by the instruction set of the hardware, right? So in other words, if I just give you the definition of an Intel CPU, like this is what it can do, and I ask you to write a program for the Intel CPU, hopefully we all agree that it does not matter what languages you might stack on top of that. The only thing they can do is reduce the number of programs that you could have written. Okay?
Yeah.
So the starting point for all discussions about programming languages should be assembly language for the chip is the primary programming language, and all programming should be evaluated against what comes out there. And that no programming language can improve on that, meaning the actual highest quality program can always be written in assembly. So the only thing we're actually asking is, by layering another language on top of assembly, can we reduce, and this is my personal metric that I would then say, can we reduce the amount of time it takes me total to produce that assembly language that I'm actually trying to produce, right? Now, so long as we stay in that realm, I think we're fine. And we can have all kinds of language discussions all day long, and we can actually sort of measure them because we can look at, like, here's the assembly we were trying to generate. How hard was it for me to get that generated in this language that I was doing? Is it very easy? That's great. Was it very hard? That's not so good. It means I'm going to waste. It means like, am I spending more time? I'll give you a concrete example. I would argue that in the old style vector notation that you had to use to program SIMD in GCC, it took longer to write your program than it did in assembly. It was because you had to do all these casts. You had to constantly cast everything back and forth. In assembly, you just write the 10 instructions you want. In GCC, you had to do all this. The mnemonics were longer because the intrinsics are longer. You had to cast back and forth every time you wanted to do something, right? And so it was just hard, right? So that was just objectively bad. But pulling back out a little bit, right? So the total cost of me maintaining this assembly language program, because that's what I'm doing. I'm maintaining an assembly language program that I'm trying to ship to people. Is that total cost less than the cost of me handwriting the assembly language? That's what I want to know when I come to this programming language. And as long as we focus on that question, I think we're okay and we can make progress, because it's not that hard for us to to do that, right? Now, what happens, I think, unfortunately, is that is literally not even thought about. Most language design occurs without even thinking what I just, like everything I just said, completely ignored. Usually what happens when they design programming languages is they're thinking linguistically in terms of other programming languages. So for example, somebody is used to programming C++, and they're like, the way I learned to program C++ is that I have these things that like are pointers, and sometimes I had this experience where I like moved the pointer like off the end of the thing and I had a bug. So what I'm going to do is, in my new language, I'm going to make it so that pointers can't go off the end of the thing. Like that's the thought process, right? That's how we're thinking. Now, sometimes that's a reasonable way of thinking. If that leads to something that actually happens to have positive effects in the metric I was talking about, less bugs in that assembly program, because we all agree the assembly program I was trying to generate was one that didn't move the pointer off the end. So if it becomes easier to generate the assembly language that is correctly moving the pointer, good thing. But if all we're ever thinking about is that way, I had problem X in previous language and I fixed it now in this one, we run the risk of constantly just working off of our own abstract linguistic constructions that had nothing to do with the original goal of generating the assembly. Now you can see that in these new languages all the time. You're like, what's this feature here for? It's like, oh, well, that's because we wanted to support this programming paradigm from this other language that we thought was cool. And I'm like, do we need that to generate the assembly? It's like, I don't know. I never thought about the assembly. I just want to be able to type code that way. And to me, that is what creates this spiral off into nowhere, because now we're not tethered to reality. We're not tethered to the problem. We're tethered to our own linguistic thinking, and we're fixing problems we may not even have because we're not using that other language anymore, right? But we haven't learned to speak our own language yet because we're developing it. So we're still thinking of the problems in the old language. And it reminds me a lot, honestly, computer language design, to use the most pessimistic description of it, it reminds me a lot of the humanities. It reminds me a lot of papers in the humanities. When you read them, they're entirely self-referential. They're like, I'm talking about this work, and the entire way that I know how to talk about it is by referring to what other terms people have used, right? Now, maybe that's productive for you in your industry, because in the humanities, what we're trying to do is talk. That's what their output is discussion, right? But in programming, that's not what we're trying to do. Like, we're trying to specifically create this assembly language program. So no longer thinking about it anymore is a big mistake. It should always start there. And then we should only talk about the other things once we've tethered it completely, to me.
So I think it's hard to dispute your starting point, and it's hard to dispute that that's not the way that language design is being developed, and the languages that are being successful are not the ones that are succeeding most in the way you describe. But that's almost a function of the fact that the actual languages which will succeed are the ones that make it in society, right? They're the ones that have that appeal the most to other people, bearing in mind that we're having an increasing percentage of the population becoming programmers. So not necessarily, time was that programmers were this very small, very dedicated sort of elite group of people, really intelligent.
Is really like you had to love programming or you weren't going to do it. So it sort of self-selected for people who'd probably be good at it. Whereas now it's just considered a desirable profession. So anybody does it, whether they like it or not, right?
People are now kind of falling into programming careers with no real interest in programming. And then they are ending up making decisions about which language to use based on sort of popularity and marketing buzz and et cetera, et cetera. And it would be nice to think that we can change the incentives in some way, but I can't see that set of pressures going in a positive direction. Like in a sense, this out of control process that's leading to problems is going to continue, isn't it? And we're going to produce more low quality software as a percentage of the software that's written in worse languages, wasting more of everybody's time.
I mean, I do think that's true, but it's true potentially only to an evolutionary inflection point that probably will happen at some point in the future, right?
Mm-hmm.
So yes, like the analogy to the humanities I think about a lot in my head. Like right now, programming is more like the humanities. It's people who don't really know how the hardware works, just sort of mostly what they talk about and most of the work they do is really just referencing other people's linguistic constructions. There's no fundamental, like the phrase software engineer really just doesn't apply because engineering usually would involve consideration for the underlying physical reality. Usually. I mean, maybe there's engineering disciplines that don't. I'm not an engineer, so I don't know. But, it's a much more humanities oriented thing right now. It's mostly kind of verbal, and there's not a lot of thought given to the underlying mathematical realities that may be well known to us. In fact, like I said, on the software side, it's very easy to know these things because they're highly documented chips and so on. It's harder in the hardware sphere because they're dealing with actual real physical reality that they don't necessarily know everything about. Like we don't know everything about quantum mechanics. We don't know, so they're kind of in a more challenging realm than we are. We have already been moved up one step on the chain. So we're clearly know what we're dealing with. I guess what I would say is that at some point, I do think, though, that we will hit that evolutionary inflection point. At some point, we will get to a place where a movement or group or set of methodologies that are actually strongly tethered to the problem we're actually trying to solve will break through. And when they do, it will become inevitable that everything adopts them. And the reason for that is that at the moment, we simply haven't done the hard work of figuring out how optimal we can go with programming languages that still output high quality machine code. Nobody is doing that work. The only example we have of it currently is in the GPU sphere. And I would say that it's a very encouraging example. GPU vendors were basically given this gift, much to the rest of our dismay, because, man, it's been hard to deal with it. But they were given this once-in-a-generation gift that all of the programs they were going to run on their hardware came to them raw. They were not compiled, right? So it was free for them to basically sit around going, how do we want to spec these language changes, and how do we want to write our compilers to produce things we can execute very quickly? And it's not often talked about, but it needs to be. They are the people, and shader languages are the language that completely revolutionized computing that no one talks about. Anybody, a Python programmer that you were talking about before, who has no idea what a computer is or what it does, can easily write a shader that runs extremely parallel and extremely fast. Why? Because the GPU vendors did the work of figuring out how you would concisely notate something that could be turned into a very fast parallel program. And nobody else has done that. On the CPU side, we have no equivalent. There is no argument that shaders are now completely adopted. People are writing programs in shaders that should never be written in shaders because they've been so adopted that they're almost over-adopted because they're so much better than CPU-side programming for the things that they excel at that you would be crazy not to write one. And anyone can write one. It just looks like basic math. It looks like a Python program. You don't have to think about anything. You're just like, I don't know, x equals x plus 2. And all of a sudden, that's running across 128 cores, 32 floats wide, and you don't even know, right?
Hmm.
And it is now completely adopted, just period. Everyone adopted it. And so I do think that we will hit an evolutionary inflection point for CPUs at some point. And the problem is we just haven't done that yet. And at that point, all of these discussions will become academic because it won't be anymore, oh, you have to choose Python and be dog slow, or choose C, and it's much harder for you to learn all these things about threading and simulation. It's like, no, it's just going to be, we actually provided you a toolkit for programming where the default is fast.
Well, anything that can be massively parallelized ought to go on something other than the CPU, right? Like if you've got an enormous amount of parallel instructions to run, you want something with an enormous amount of cores.
But everything has an enormous amount of parallel instructions to run.
Well, but lots of the stuff that we do is inherently a sequential series of steps. It's like the critical path.
Almost nothing we do is an inherent series of sequential steps. In fact, I challenge you to do almost anything that is literally a series of 4 billion sequential steps. It's almost impossible. And the reason for that is because humans can't conceptualize anything even remotely like that. So typically what we do is we use loops over many things. And every time there is a loop over many things, it is very rare that it can't be parallelized, at least at the instruction level, meaning SIMD, but usually it can also be parallelized at the thread level with very minor changes if you need changes at all. Sometimes you do, sometimes you don't. What we don't have is a language that makes it likely to express what you were doing in a way where the parallelism is easy for a computer to determine. Right?
Yeah, I guess. Yeah, I'm trying to think through what is it that made me think about life as mostly being sequential steps. I think it's probably that things that can be effectively parallelized end up being a library call quite often. So by the time you're writing code, a lot of the stuff you end up doing is so in the world of, okay, if you're writing a game engine, which you have been, then yes, a lot of it will be doing all of the parallelizing. But if you're writing the game, then most of the stuff you'll be doing will be short pieces of logic that pass, top to bottom through a function. There's no point saying this series of 10 quick things that this one unit is going to do this frame. I'm going to try and parallelize it, like just run them in order. Maybe I'm wrong.
I can tell you two things related to that example, if you would
well,
like.
I'm sort of thinking out loud. So now I'm thinking, okay, in an imaginary thing where you've got a load of units, actually all of them are probably running that short set of instructions in parallel.
Right, I was going to say two things. So number one, like I said, it's not really possible for a human to conceptualize 100,000 units, all of which are running completely different code. Because if that was true, you had to write 100,000 and then the update functions. No one's going to ever be able to balance that game, right?
No.
So you know that many units will be running similar code paths, which could easily be vectorized, right? Number two is that, well, okay, so suppose that unit's running code that's totally different than every other unit. Well, what's to stop another CPU from updating a different unit, right?
Yeah.
And so usually when you look at code, the problem is not that it couldn't have been parallelized both wide and multi-thread, but rather that the way we write these programs, there's no way for a compiler to know that. It doesn't know, right? Because sometimes some of those units are going to do something like apply damage to another unit, right? Now, it's pretty easy to construct a parallel program where that can run parallel and that gets resolved at some sane place. But a compiler can't do that. It doesn't know how it would reorganize the code to make that make sense. Now, if the programming language instead had been like shaders, where typing in game entity code naturally leads to something where things like updating cross-entity are in a separate section because that's the paradigm for this programming, or that programmers, when they were taught, understood that writes to other entities happen at the end. All of a sudden, now we can do all of that work. So the problem is not that there are actual serial dependency chains. The problem is the compiler doesn't know where the serial dependency chains are, because writes to and from memory could need, for all it knows, you wanted those to be sequential. 99% of the time they didn't need to be, but it doesn't know. It doesn't know which the 1% are, right? And so pretty much any program you run today can definitely be parallelized, both SIMD and thread. It's very rare to find one that can't, but it's not possible to do it automatically. And that's the real challenge going forward for these languages. Which coincidentally no one's working on. So that's great.
Great. So another thing I wanted to discuss was AI, I guess is the kind of popular term for it. Machine learning may be more helpful term. In particular, not with regards to code generation and all of that malarkey, but the fact that it seems like there's an increasing amount of cases where you can actually use a machine learning solution to produce more effective, more performance code that achieves its task better than the handwritten alternative. The example I'm thinking of is Alpha. What was the is it AlphaGo? What was the chess one? Right, the
AlphaZero.
AlphaZero, yeah, which did way better than Stockfish. So you've got the basic problem of write an algorithm that plays chess. The traditional approach was you think really hard about the problem and write lots and lots of lines of logic, and you iterate it over years. The new approach is you just set up some kind of neural network and give it loads of compute power and loads of time, and it will eventually produce the best result. I've seen experiments doing the same thing. For example, how given this spec for a CPU, how do you implement it in silicon, right? Rather than that compilation process being something that's done with lots of logic and lots of handwritten stuff, you just give it to a bit of machine learning and it comes up with something we don't understand, but is better. So, but the skills that are required for this type of algorithm development are completely different from the types of skills that are required for traditional software engineering. You know, you've got to understand about the type of data that you're feeding in, and you've got to understand about the architecture of your neural network, and that's about it. So are we going to see the rise of a new discipline that will end up replacing, like, how much of the software industry is eventually going to be replaced by this new approach of using machine learning techniques?
I mean, I don't really feel like I have an answer to that question. The reason for that is I don't work on AI, and what you're asking for is more or less like a forecast, right?
Well, yes.
I can tell you for sure that the machine learning models that they have presented thus far can't really replace almost any programming. And the programming that they can replace are ones that we already had algorithmic optimization for. For example, there's Stanford, for example, had a paper where they showed a Metropolis algorithm solver that produces much more optimal code than a human for a small assembly loops, right? Which is basically all you could hope for from one of these machine learning things.
But so what about like
So I guess all I'm trying to say is what you're asking for is a forecast of like, okay, to what could we scale that, right? And the answer is today, nothing. Optimizing small loops is about what we could expect to scale it to. The question is, what can we scale it to in 10 years? And I feel like in order to have a good forecast for that, I would need to be working on AI, because there's naturally, in any sort of thing like this, there's a question about what is the current asymptote without some important algorithmic update that won't necessarily happen in the normal course of doing things, right? And so I think it's highly likely that there's at least one more algorithmic improvement necessary before modern AIs can tackle much real programming, just based on how little they understand of programming right now for the general AIs that are out there. There's probably one more algorithmic improvement, because they're already using, $50 million of CPU time to train one of these things that can't program at all, right?
Mhm.
So it's not like, oh, we'll just spend 100 million and I'm sure it'll be fine. It's like, okay, you're already like way at this upper bound. So I think there's definitely some algorithmic improvements that probably have to happen. And so what you're asking for is for me to try and guess, will those algorithmic improvements happen? And if they happen, when will they happen? And I just, without working on AI day to day, I just don't have a forecast for that. It could be that we get those algorithmic improvements next year. It could be that we don't get them for 50 years. We have no idea, right? And so people working on AI, they might have a guess. They might be like, yeah, these things are looking very promising, and I think they will happen in the next N years. But without that kind of intimate knowledge of the domain, I really don't have an interesting answer for you.
Yeah, I wasn't thinking so much in terms of let's see language models writing code as so more examples in kind of the world of games. The way that you animate a character moving maybe traditionally has been, you've got a state for running, and then you've got a state for sort of walking sideways, and you do a transition between them, and it's all very hand solved. But it seems like that's being replaced now by you just train a neural network to understand how to animate a character. Likewise, cloth simulations. We use a load of GPU time to do a physics simulation, or you train a neural network to predict a cloth's movement, and you just run it's very much quicker to run the estimate of the cloth simulation.
So I guess I would say that looking at those sorts of things, I'm not sure there's much of interest there. I mean, maybe there is, maybe there isn't.
Rendering's another case. I've seen people do crazy estimates of reflections and refractions and volumetric whatever. That's, again, you train up an ML agent instead of doing all your actual lighting calculations.
Yeah. So I guess the way that I would say that is, it really depends on what your goals are. And also just some of it depends on just like why you decide to adopt something or not. So let me take the case of the character animation.
Mm-hmm.
We've had for 2 decades now, algorithms for doing automated analysis and motion transitioning that has existed since at least 2004, that you can just write. It doesn't require all the crazy ML stuff. It doesn't require any of that. You can just literally write them.
Mm-hmm.
The number of games that use it is like close to 0. Why? I have no idea. They just didn't want to write that code, right? So I think in those domains, I think the question of will people adopt ML for this really just boils down to, will someone package it easily for them? If someone had packaged that technology easily for them, they'd be using it now. If someone packages the ML easily for them, they will use that. But really, is there a huge value add there? Not really. Like, I don't see, especially not character animation, I don't see there being much of a value add, because we've had a lot of good technology on how to do that stuff that doesn't involve ML, and nobody used it. So it's really just a question of packaging in those domains. Now, in other domains, that may not always be the case. For something like sample integration, which I think is what you're talking about when you're talking about rendering, how many rays per pixel do we need to cast to produce a good image? Humans, traditionally have not seemed to come up with particularly great algorithms for using low numbers of raycasts to generate smooth images that mostly work a lot of the time, maybe sometimes, cross your fingers, right? It seems like ML is better at that task than humans were. And so that is a case where ML is arguably providing value we did not previously have, meaning it is producing an algorithm that humans had not stumbled upon or intentionally created, or however you want to look at it. And that's actually valuable. Now, from my perspective, it would be more valuable for us to go decode what the neural net is actually doing, because chances are we can probably improve it intentionally, because we know a lot of things that the ML algorithm doesn't, like math or how light works, for example. And we might be able to improve it from there. So I would prefer that route. But I do think that it's making a contribution, meaning there's something we can learn from this, even beyond just we could use it. We could also, I think, learn something because we're missing an algorithmic space that we probably should know about and understand.
Okay, interesting. But I guess my point was really 10 years ago, if you were a light transport researcher and you were going to do cutting edge work, say you were going to go and work for, I don't know, Sony and develop some new rendering technology, your technique for doing it would be to do the maths and to understand light, maybe do some experiments and develop an algorithm. Maybe it was more of an optimization question. How do I get this existing technique to run faster? I think if you're doing light transport research now, you're much more likely to be developing something using machine learning. And I think the same is going to be true, say, building a compiler. You've got some input, which is the source code, you've got some output, which is the intended binary, and you've got to, well, not even the binary, I guess. The output is actually the results of the code running. And in fact, partly that is given this expected input data, right? We're not just running this code in a vacuum, we're running it given real humans and the types of data that they're expecting to come in. So the compiler actually is going to do much better than humans before very long, regardless of what mathematical discoveries we can stumble into, because we've seen in the case of chess that our best attempts to optimize this algorithm fall down completely flat compared to the best that machine learning can do. So I just see an increasing number of jobs making that transition across from hand-rolled code to nursing a CPU to develop a solution.
I mean, it's a one-off though. So if basically what we're saying is you think that machine learning kernels will be sort of inserted at each place of the pipeline, that they currently don't exist for any particular thing, let's suppose that's true. That's a one-time job. After that's done, there's nothing else you can do. That's it. Because all you knew how to do was put a machine learning thing in there, right? So the only job left after that, if you believe there will be a job, because maybe there isn't, and we just say, well, it's good enough. Whatever the machine learning does, it does. The only job after that is figuring out what the machine learning is actually doing so we can figure out how to improve it. If we don't know what it's doing, or we don't have somebody figuring out better stuff than what it's doing, at least in some cases, we're never going to improve it. So the job basically remains the same. If my prior job was I need to look at the output of this multi-pass optimizing compiler and figure out where it's producing bad code, well, the job is exactly the same once the optimizing compiler's passes include an ML pass. Now I just include the idea that when I want to make a fix, I have to know something about how the ML compiler is actually working. ML meaning machine learning, not ML the language, obviously, but
right.
Gets a little confusing there, right? And so, it's like, okay, but is that really that much of a change? Maybe it is. I don't know, but I
Well,
mean,
if
like, it's not as exciting to me as people seem to make it. I'm like, okay, so it's like, yeah, we've got these little high. So basically, the way I think of AI is a very large sort of polynomial be the wrong word for it, but it's a very large multi-factor kernel that I evaluate that gives me an output, which is an easy way to get a point sample in some space. That's a space I'm looking for an answer in. Okay, I mean, we've had that forever. These are just better than the ones we had before. Does the job change that much to me? Not really. It's a nice tool because it means that if I'm having trouble, if there's something where I'm like, I don't really know the algorithm that I could apply here, like we don't have a good one, it's just another tool in the box. Like, okay, well, maybe if I have access to machine learning, which, that industry's job right now is to do that for me, is to make machine learning be something I can use as a tool. Right now, it's not. The only people who could use it are people who can afford $50 million of CPU time, right? But, the job of that industry is to figure out, A, can this be done at scale, meaning so that every programmer could use it on problems that it hasn't already been used on, right? And B, can that be, made efficient enough to make it better than just the human sitting there? Let's assume they succeed. Then it's just another tool. It's another tool for me to use when I am trying to make something and there isn't an obvious way that this should be done. Maybe the ML can figure something out. To me, it's always better if I then look and see what did the ML thing do and why weren't we looking in that place, because that may pay additional dividends, at least until the MLs have to get really good before I think you don't need to do that thinking.
If you look at the production, so imagine a layout on a piece of silicon of a specification made by ARM, right? ARM says, here's the logical description of how our next CPU should behave. You've got to figure out how to lay this out, and humans write software that does that translation job. And we understand how that translation is done because it was written by people, and therefore the results that it comes out with have some kind of logical properties that we can understand. Probably the optimal translate, maybe a compiler would have been an easier example to pick, but let's stick with this for now. Probably the optimal piece of software that does that process is not understandable to humans. It's probably gigabytes worth of uninterpretable gibberish that at some point will go over the heads of any human to understand. I would think. It's just an inherently complex, multi-dimensional problem, which we have brought down into the realms of human comprehension to use. But I think there must be solutions for that problem that are better, but are beyond our ability to understand.
I doubt it.
Okay.
The reason that I doubt that is because I think the realms in which, just because of what AI looks like, my assumption would be that will only be true in realms where the fitness function for whatever the thing is you're trying to actually make are themselves judged by things that look like neural networks. So for the rendering case, I do think that's highly likely, because it may be that the explanation for what makes the best thing for reconstructing images that a human doesn't notice artifacts in is something that processes images like a human, which would be a neural network. The thing that creates the most optimal layout for a chip is like an actual hard physical constraint that has nothing to do with the neural net at all. I find it very unlikely that the optimal way to do that layout is actually going to be something which is just a giant fuzzy, it feels like the chip should go here, which is what an AI is basically doing. Based on billions and billions of runs, it's like, well, I know that the last time I laid down something like that, it didn't go so well, so I'm not going to do it this time. I doubt that any sufficiently advanced version of that can't then be reduced dramatically by going, oh, actually what's happening here is we can reduce that entire cluster of things the ML was doing. Again, the machine learning, not ML, the language, that the AI was doing, into something more compact, like basically compressing the AI down. And the reason that I think that is just because it doesn't seem, when we look, I mean, when you look at nature is essentially running its own massive optimization process. When we look at nature, it doesn't really seem like it requires massively complex things to produce optimality or near optimality. Like, I don't know, maybe I'm misinterpreting that, but it sure doesn't look like it. Nature tends to just do complexity because it can, not because it has to, right? Like,
there are certainly simple problems that have complex solutions, right? So something, you know, something like the traveling salesman problem. Isn't there a certain fungus that you can put down that will naturally produce a network across? If you put dots of sugar around, it will then do the equivalent of, like, you can put dots in the shape of key cities across a country, and it will naturally produce a shape that resembles the traffic layer, like the major highways in the country that you're talking about. So you what I'm saying is there's a mapping sometimes between nature and software problems for which the true optimal solution is non-polynomial. You could imagine an optimization problem like design the most aerodynamic wing, which seems to be that there isn't a simple algorithm to do it. And actually, I think they have applied machine learning techniques to that produce very weird shapes that are better than anything that we've produced theoretically, as in from our known set of algorithms, we can't produce something as good as we can. And ultimately, producing a CPU is quite similar to an aerodynamics problem because you're dealing with thermals and the strength of parts. You've only got a certain tolerance on the machine, and you don't want magnetic interference and all these kinds of, like, my intuition is that producing a layout of a chip has the same sort of properties as a chaotic system, where simple inputs and complex outputs, and therefore the best you can do is make a guess at a solution.
Well, I guess what I would say is I wouldn't tell you that you're wrong, but I would tell you that you're pessimistic.
That's probably fair.
Computational complexity analysis has been with us for less than 100 years, I would say, right? I mean, you're talking about something that came to prominence in like the early 20th century, and we're not even out of the 21st century yet. In fact, we're not even halfway through, right? So I think that kind of presupposes a pretty pessimistic view of human endeavor going forward. If the idea is that, well, ML is kind of the end of it for us, that's the best we're going to do because guess and check is all we've got. Now, you might be right. It might be that, like, that is the end of human endeavor, algorithmically speaking, and we're never going to invent a new kind of math, and we're never going to invent a new kind of computer, and we're never going to invent the weird dark energy superposition drive that can evaluate every possibility at the same time, or all these other things are just never going to happen. And maybe that's true, but I would say, like, two people talking about a podcast in 2023 making that judgment call sounds pretty pessimistic to me. It's basically foreclosing the entire set of possible things that may turn out to be possible that just don't seem likely because we don't know any better right now after 80 years of trying. I mean,
it seems like
really?
maybe a fair more reasonable prediction is that in the short term, it looks like there's a lot of sectors in software that are going to, at least temporarily, fall into the domain of ML solutions that previously have been traditional classical algorithms.
Yeah, I would, and I would say, yeah, I would put an asterisk on that though, which I was trying to kind of put on it before, if you would allow it.
Sure, sorry.
Maybe not. It's your podcast; you don't have to.
Go
But
ahead.
the one thing I would add to that is, it's not an apples to apples comparison. Many things that people are using ML for now, they never tried half of the other algorithms we could have done because there wasn't momentum.
Mm-hmm.
And so one of the things that I think you have to understand about ML is one of its biggest advantages is not it, but its momentum. The fact that people are excited enough about this technology to be willing to spend billions of dollars seeing if it works is by far its biggest advantage. The reason for that is we've had the ability to do super optimization in compilers forever. It just never happened. Nobody is willing to put in the time to do that. When something, because the Metropolis algorithm isn't a buzzword, right? I can't sell that to you as being exciting, but I can sell you ML. ML has buzz right now. So it will put optimizers, which is what these things are, in places where they weren't before. And part of the value add there has nothing to do with whether ML was better than some other thing we could have done. It has more to do with just the fact that it's got momentum and a clear way that people can make money from it. So if I teach you how to make a Metropolis algorithm optimizer for your problem domain, you can go write that, and that's the end of the story. If I force you to use ML as the optimizer in there, I can charge you millions, hundreds of millions of dollars of cloud compute. Well, that's more interesting in a capitalist system, right? So, I mean,
that's interesting.
I would put an asterisk on ML in that some of the things that it's doing are clearly improvements over the status quo. You mentioned chess or Go, and that's, people were trying that legitimately, and this was better. Other things like code optimization, okay. I mean, not really. The current code optimizers are garbage, and no one's really trying. So,
compression algorithms, AI have beaten the state of the art for image compression, as I understand it. It's interesting. I think we're going to have to accept some losses in the battle against ML.
Well, like I said, the games are the clear loss, like for obvious reasons, right? I mean, like it's better at chess and Go than any human algorithm was, and I don't think anyone currently disputes that.
But then games, in a way, are deliberately a set of rules designed to be interesting and difficult to humans. So maybe we shouldn't be surprised that a different type of intelligence does better at games. It's like a type of problem deliberately designed to be at the boundaries of a certain type of our capacity. And if we were designing games for ML agents, we'd probably find them easy in return, because it would be
I don't know about that, but okay.
Just saying.
All right.
Well, in a way, a game is targeted at a human brain to stretch it, and therefore it's the type of problem that's quite likely to be easy to beat by an alternate route than asking a human to do it. There's one last thing I wanted to ask you about, which lots of people in chat were asking about how they should go about getting educated if they want to become good, effective programmers, the type of programmers that we have been hoping for, that will storm in and save the day and write good code for a change. I know that your series of videos wasn't actually started as intending to be educational content, but am I right? You've started working on Starcode Galaxy to be a deliberately educational project?
Yeah, I have some stuff in the works that's designed to sort of do this. One is that I do have a Substack now where I'm going to be putting up some performance oriented stuff for people. And that's just at computerenhance.com, www.computerenhance.com. And that will be live February 1st. I'm trying to have those. That's the short term stuff. Star Code Galaxy is a longer term thing that's a much bigger project, which won't be out in the short term. So it's not really going to help people right now. But yeah, coincidentally, the first thing that I'm doing on the paid Substack thing is going to be a series on performance awareness, which to me, that's the biggest thing. Because I think, again, I really want to hammer home the fact that micro optimization is not what is required here. People, they think about optimization and they're to them, because they don't have experience with it, they're thinking that the only way that code gets faster is by someone knowing like every little way to write this assembly code to get this thing to happen, right? Like it was kind of in the old days where these people, to try and write a game on a Commodore 64, they were doing all this crazy stuff. But I don't really think that's what's required anymore, because hardware is so like powerful now that really all you need to do is kind of get out of its way, right? And so what you need to do is learn those concepts that the assembly programmer would be using, but you don't have to ever get good enough to actually use them. You just have to know roughly what the CPU is doing. And then you can make these high-level architectural decisions that are easy to make, actually. You can make those decisions correctly. And then, unless you are going head-to-head with some company that's got a bunch of micro-optimizers, which nobody does. So what's the, I mean, that's just very rare, right? Maybe in games, but even then, rarely. If you're just talking about a normal, today's competitive environment, just making those high-level decisions better because you're aware of what the CPU has to do and what's involved, that's all you need. So half of the work has been taken away. You don't have to learn to program in assembly language anymore.
I feel like if you get your data structures right, you're 90% of the way there.
In a lot of cases, yeah, it's about it's two things really. It's getting what the data looks like correct, and then also structuring in whatever environment you're creating the code in, structuring it so that it can be made to run fast. There's a lot of things you can do when you don't know about the underlying hardware and how it works. There's a lot of simple, innocent looking things you might do that actually make it completely impossible to optimize this thing, right? And you could just as easily have chosen the easy to optimize thing, but you just don't know, right? You just don't know how much worse it's going to get if you do that. And so just a basic awareness of those things is mostly what I think is missing. And I don't think it's an insurmountable challenge. I mean, talking about some continuing ed for programmers for a few months is enough to get it in your head. Like, okay, I can sort of see, I get what he's saying. Like, we just need to make sure we stay in these sort of like things batch size wise, or this sort of thing, like just these couple things I can do that aren't a huge deal, and we can go from there, right? And then regrettably, there's still the other half of it that's like, yeah, if you really want to attack some problems, you need to learn the nitty gritty. But that to me is more unrealistic. I'm not expecting everyone to put in the hours to learn that stuff, because it's just not realistic, I think, at this point. The first half, I think it's realistic to learn the basic performance characteristics of a machine. I think any programmer can do that, whether you're programming in Python or assembly language.
Yeah, if you're running into a problem where you've written something that's genuinely slow and you don't know what to do, and you've tried your hardest, that's already, you're in the 0.1%. Most of the time it's just people not bothering, people not thinking about it, people being lazy, basically. So if we can, if everybody who's writing software was putting 10% of their brain power to thinking about performance, then I think that would basically be it.
I think you're totally right. And again, that's because we don't need all the performance to make a very substantial, very meaningful impact in the quality of software that we use today. Getting 10% of the performance would be huge because there's so much on the table. 10% of the performance on the table today is like 10 times faster software. Like 100x, 1000x are not unreasonable speed gains to get from a lot of software today. And so, it just, you don't have to become an expert. A little bit of knowledge in this area could go a long way. And so I think the focus right now should be, how do we just get that little bit? How do we get most people knowing enough to sort of like, just do those few things? And I think that's, that would be great, right?
Okay, well, tell people your website again, and also your YouTube channel, and anything else you want to point people to.
www.computerenhance.com. That's it.
Computerenhance.com.
You can get there, and I'll.
Amazing. Well, Casey, thank you so much for joining me. I'm really grateful, and I love talking to you. So thank you.
Oh, it's been a pleasure. Thanks for the interview, and thanks for putting out a podcast for everybody. It's great.
Great.